Welcome to the first colloquium of the semester, right? I hope you're all back in the swing of things already. For those of you who don't know me, I'm Steve Hankovich. I'm an associate professor in the department. Shatir actually runs this colloquium series, so I don't want to steal his thunder, but I'm today going to introduce our speaker. And I think we'll be set up with chairs. That's what the little delay is about. If we're missing any chairs, somebody comes in, just holler at me, we can find one.
Like an overbooked flight.
Yes, I know. We keep telling them we need larger rooms for our department, but we don't get them. So it's not yet. So anyways, so it's my pleasure to introduce Mike Wakin, who's our speaker today, and we'll kick off the colloquium series. Mike's an associate professor in the Department of Electrical Engineering here at Mines. He got his PhD in electrical engineering from Rice. I won't say when. I typically don't want to do that. Like, I'm being introduced, I'm like, don't tell anybody when I got my PhD, please. He did a postdoc at Caltech, spent some time in Michigan, and then came here to Mines after that. He was a Ben Fryrear Associate Professor, which is a prestigious chair to hold for the past 3 years until this year. Now it's sort of rotating basis, so I'm sure you'll be that again in a few years. His research interests include sparse, geometric, and manifold-based models for signal processing and compressive sensing, which I believe, at least a few words are in the title of the talk, so that's good. Mike has many great awards. He was presented with the DARPA Young Faculty Award in 2008. He got the NSF Career Award in 2012. These are all amazing honors. And he received the Excellence in Research Award as a junior faculty member here at Mines. So I will stop going on about all of his accolades and let him speak. So thank you very much for joining us, Mike. Appreciate it.
Thank you, Steve and Shatir, for the introduction and the invitation today. Thanks everyone for coming. There's a lot of familiar faces in the audience. That's always nice to see. For those who don't know me, so I'm an electrical engineer. My research involves primarily mathematical models and algorithms for signal processing. And when I say models, mostly I mean models to try to capture the kind of intrinsic low-dimensional structure in high-dimensional signals and data sets. When we have good, efficient models to describe signals, we can use those models to remove noise, we can use them to compress signals, and we can use them to solve various kind of inverse problems and parameter inference problems. And so a lot of my work has applied those kinds of ideas in the field of what's been called compressive sensing, where broadly speaking we use kind of efficient randomized sampling protocols for capturing high-dimensional signals and data sets using small numbers of random samples and then potentially reconstruct all the data that we didn't see. This talk is not sort of exactly a compressive sensing talk, but it's in that same spirit. Before I go on, this is joint work with my current PhD student, Shuang Li, former PhD student from Michigan, Jay Young Park, and Anna Gilbert, who co-advised Jay. Dewei Yang was a former PhD student here, and Gongguo Tong is also a professor here in electrical engineering, and we've been working together on a lot of problems that kind of branch out from what I'll talk about here. So in the spirit of kind of sampling and compression, we're interested in some theoretical problems that were motivated by practical problems that arise in fields like structural engineering and civil engineering, particularly structural health monitoring, where we'd like to monitor the health of some structure like a building or a bridge, kind of say collect samples of data, maybe vibration data from these structures over time, and use those data to infer the health of the structure, identify potential problems or damage or fatigue, flag the structure if it needs to be shut down for inspection, and so on before failure. There's growing interest in using wireless networks of battery-operated sensors for these types of applications. So these sensors would collect vibration data over time and, let's say, transmit that to some central node, and the central node would do the processing to assess the health of the structure and figure out what are the sort of important parameters of interest. And from our perspective, we're interested in providing some theoretical guarantees to guarantee how accurately you can assess the health of the structure, or more specifically, how accurately you can estimate certain parameters that are relevant in the field of structural health monitoring. And meanwhile, we'd like to do this from as few samples or as few measurements as possible, kind of to minimize the sampling burden at each one of the sensors in the network and to minimize the amount of data that has to be communicated to some central node. So all the problems that we'll talk about today all fit into the same kind of model. So imagine that we have a structure, say, equipped with n sensors. So something like a bridge, and we've got n different vibration sensors on that bridge. Each one is measuring, say, a displacement signal. It could be acceleration. Everything I'll say actually applies to acceleration as well, but let's just say it's displacement, maybe vertical displacement at sensor number 1 over time, displacement at sensor number 2 over time, and so on. N total sensors. Throughout the talk, N is always going to refer to the total number of sensors in our network. At any given time t, we can imagine stacking these displacement values into a vector. And since that vector depends on time t, we'll denote that by x of t. Now, what do we know about x of t? Many physical structures can be described by a second-order differential equation of the form we see here, where the time evolution of x of t is described by this equation. We have x, we have its first derivative and its second derivative with respect to time. And also in this equation are some matrices, the mass, damping, and stiffness matrices that are characteristic of the structure that we're studying. Those things may or may not be known in any particular application. And on the right-hand side is g of t, which in general is a forcing input that's being applied to the structure. And for the sake of simplicity, we're going to assume g of t is 0 in this talk. So it doesn't mean the structure is not moving. In particular, we imagine that it is moving, but it's only reacting to some previous set of initial conditions. You may have had some past input, like wind blowing against a building or traffic driving over a bridge. Now that's gone, and you're watching the system react to that. So it's vibrating in response to that. Under that simplifying assumption, this free vibration assumption, we know that the solution to that second-order differential equation looks like this. And this equation says that x of t at a given time can be written as a combination of some number k of vectors, we call phi k, and what those are called are the mode shape vectors of the structure. They're kind of an intrinsic characterization that come from those mass, stiffness, and damping matrices that I talked about on the last slide. We'll say more about these mode shape vectors, but they're fixed for the structure. So as x is changing over time, what is changing on this side are the coefficients, the weights attached to these different mode shapes. In particular, those will, in general, act like sinusoids. Each one will have its own kind of characteristic frequency, but they'll die out over time. They'll be damped by some exponentially decaying envelope. So to make this tangible, this is based on some data collected by the group of Jerome Lynch in Ypsilanti, Michigan. And they went out to this bridge. They put 18 different vibration sensors on that bridge, and then they estimated the mode shapes and frequencies. They found that there were k equals 3 dominant mode shapes in the structure. That's what's shown in these 3 pictures. And that the coefficients for each mode shape oscillated at about this frequency. So about twice a second for this one, and about 10 times a second for this one. In other words, to a good approximation, at any time, the actual sort of displacement profile of the structure was just a combination, a weighted sum of these 3 mode shapes. And over time, the weights change, say, 2 times a second, right, for this one, and so on for the other ones. And then these things die out over time. So all that's a little bit of background to set up the problem of what's called modal analysis, which is given samples of these vibration signals, these X signals over time, let's say at m different points in time, we'd like to estimate the modal frequencies and the mode shapes of the structure. This is useful in structural health monitoring. In particular, let's say you build a structure, you know it's healthy, you could estimate the mode shapes and the mode frequencies. Later, if you detect that there's been some kind of change in the modal shapes, that may reflect a change in the structure. Possibly it's gotten fatigued or damaged. You may even be able to localize where that happened based on which part of your mode shape has changed. So that's a very, I'm sure, oversimplified explanation of how they would use these in assessing the health of a structure, but they are relevant. With that said, kind of the core mathematical problem we're setting up here also has a number of applications in signal processing. And so you could think of this kind of civil engineering angle as just one way of motivating these kind of same core mathematical problems we'll talk about today. So our goals will be to use this data to estimate these modal frequencies and mode shapes. We want to minimize the number of samples m that we have to collect, so that the batteries will last longer in the sensors, and so that we have to use less communication bandwidth as we send this to the central node. And we'd like to also explore different kind of compression techniques, that this data might be compressed before you send it to the central node. And we want to do all of this with some provable guarantees on how accurately we can actually estimate these mode shapes and frequencies. Now, this is a good time to mention that modal analysis is not a new problem. It's widely used in structural dynamics. And there's a number of algorithms out there that have their various advantages. Some of them are based on sparsity. Many of them are based on statistics, kind of source separation or independent component analysis-based techniques. Not all those require the structure to be in free vibration. They all, as I say, have various advantages and disadvantages. Our angle on all this was that we were really trying to find things for which we could really have some solid theoretical analysis, which I think is a blanket statement in that field tends to be lacking. Right? There's a lot of good algorithms for which there's kind of a lot of hands-on knowledge, but relatively few theorems that we've encountered. So we're going to make one more assumption, which is that the structure has no damping. Now this is a physically unreasonable assumption. No damping would mean that these sinusoids do not decay over time. They just continue oscillating. A physical structure that obviously wouldn't satisfy that. It may be a reasonable assumption over short time scales that there's not significant decay in these sinusoids. We're going to talk about two methods for doing modal analysis. One of them, as we'll see, actually turns out to be robust enough that this assumption doesn't really hurt it. And the second one I'll mention at the very end of the talk. We're looking at ways of kind of extending that framework to account for damping. Okay, but under that assumption, our signal x of t, as I said earlier, can be written as this weighted sum of these k mode shapes. And here are the coefficients. Now these are sinusoids, but they're not written as sines or cosines. We chose here to write them in their complex exponential form, right? So if this is unfamiliar to you, just think of it as kind of a complex version of a sinusoid. Each one has its own frequency, f1, f2, up to fk. The reason we do this is for mathematical convenience. It's more convenient to have this signal in complex form. But it is practically reasonable to argue that you could construct this version of the signal. So this can be accomplished in a physical system using a Hilbert transform filter that removes the negative frequencies from the incoming signal. This happens a lot in electrical engineering and communication systems. So in various parts of a communication system, there's kind of conversions between signals in complex analytic form and in real form. So that's what we're talking about here. The last thing in this equation are the amplitudes. So while the frequencies and mode shapes are intrinsic, they're characteristic of the structure, what the amplitudes in this equation depend on are the initial conditions. So depending on where your structure started, the only thing that would change in this equation would be those amplitudes. So in general, all of this is unknown, and from samples of this data vector, we'd like to estimate all the parameters on the right-hand side, especially the frequencies and mode shapes. Now that we've taken damping out of the problem, it's worth mentioning that this connects to some other kind of classical problems in signal processing. In the compressive sensing field, somebody might look at this problem and say you have n signals, and each signal is sparse in the frequency domain because it only consists of a sum of k different sinusoids. And each of these n signals shares the same k active frequencies. You could set this up as like a so-called distributed compressed sensing problem where you want to jointly estimate these k frequencies. Unfortunately, the standard compressed sensing framework requires, for that to really work, you need all these frequencies to be on some regular grid. They all need to be like multiples of some harmonic frequency. We're not making that assumption here. We're solving the so-called off-grid problem, where the frequencies are not all harmonically related. And then just to mention here, as I said earlier, this kind of same core mathematical problem has other applications in signal processing. So one of those is in array processing. if you have like a linear array of antennas and you have different signals coming into those antennas from different directions, and you'd like to localize what are the angles of arrival from each of these incoming signals, you can formulate that problem in a way that looks exactly like what we've got here. The analogy is that K is the number of sources coming into your array. M, for us, the number of time samples, corresponds to the number of sensors in your linear array. And N, which is for us the number of sensors, is the number of time snapshots in the DOA problem.
So, Mike,
Yeah.
I have one quick question. If you go back one slide, so what's the value of n? Like how big these vectors are? Is that 20 in the order of 20, 10, 20, or?
Yeah, that's a good question. I think we're trying to provide some guidance on that. I don't know for good practical problems what would be, as I'll talk about kind of one of the theorems that justifies these techniques is asymptotic, like as m goes to infinity. Right? So we're trying to provide some answers on how small you could really make.
And also this x1, x2 up to xn, those will be correlated, right? Some
Yes,
sense?
they are potentially correlated.
So
yeah.
you are going to look at the coherence also in some way, because given.
Yeah, so one way that could end up being expressed is in terms of like correlations between the mode shapes themselves. So we will characterize for different techniques whether you need these mode shapes to be orthogonal or not. That's kind of one. But otherwise, we're not really worrying about coherence between the different sensors. It wouldn't say necessarily hurt you to have two sensors at the same location. I don't think that would break anything that we're doing here.
So if you put it in phi, then the coherence would be stationary in time in a sense. Because the phis are independent of time, right?
The phis are independent of
So then
time,
if you want to put it there, then the coherence is independent of time.
like a spatial coherence, I guess you would think.
Yeah.
Yeah.
So not a,
Temporal.
so yeah, he was thinking about temporal.
Okay.
So that was great, okay, sounds good.
Any other questions before I continue? Yes.
I don't have a question, but maybe a comment.
Yeah.
In this room, we're used to seeing that J thing that you've written up there. We're used to seeing that as I.
Uh-huh.
So making sure that everybody's, we're still audience.
Yes.
So
So-
we're seeing that J as I instead.
In electrical engineering, not that I do many circuits anymore, but I represents current in electrical engineering. So yes, thank you for clarifying. The J is the square root of -1.
So I had a question about where you're assuming sparsity.
Yeah.
We won't be seeing any sparsity assumptions on your fees, on the mode.
That's correct. We won't be
Okay.
making any assumption like that.
Okay.
Really, I think it's fair to say the only way that sparsity is arising here is that K is generally relatively small. Like for that bridge in Michigan, it was about 3, but you had only about 3 active modes.
Okay.
So we'll see how the kind of complexity bounds scale with K as we go. So what we're going to talk about today are a couple of ways of attacking this modal analysis problem. Both of them are based on matrix decompositions, as we were talking about at lunch. So here's the matrix that we're really interested in. We just call this the data matrix. We have n sensors, and let's say they're each collecting their displacement value at m points in time. Then we could build this n by m matrix that we'll call capital X. And all the modal analysis techniques we'll talk about involve various kind of factorizations or ways of decomposing this matrix X. These decompositions will kind of reveal the parameters that we're interested in. And as a reminder, we'd like to keep m as small as possible and also explore kind of other ways of compressing this matrix. So the first method we'll talk about is a classical one in modal analysis, maybe the most classical. It's just called the proper orthogonal decomposition. This shows up all over science and engineering under different names. It's very simple to describe. We take this data matrix X, one step. We simply take the singular value decomposition, or SVD of X. I'll show a picture of that on the next slide. When you do that, the left singular vectors of that decomposition are also called the proper orthogonal modes of the structure. And it's long been known that these proper orthogonal modes can actually themselves just approximate the true mode shapes, the things we're trying to estimate of the structure. So as I talk about POD here, we'll only be talking about mode shape estimation, not modal frequencies. We'll get into modal frequencies in the second part of the talk. So here's what doing the POD looks like. You take your data matrix. When you compute an SVD, that delivers to you these three matrices on the right. The first one has normalized and orthogonal columns. The second one is diagonal, and the last one has normalized and orthogonal rows. And when you do this, when you apply this algorithm, you just extract this matrix and you look at the columns. And interestingly, those columns can actually approximate the true mode shapes of the structure. That's been known for some time, but as I said, the results on that were asymptotic. That required the number of samples m, or the width of your data matrix x, to go to infinity. And so what we'll talk about are some non-asymptotic sampling bounds that we developed that help us understand kind of how compact we can keep this data matrix. I'll state the first result on the next slide, but it involves the setup here. So we're going to assume that these m time samples are collected uniformly in time, and the interval between consecutive samples we'll call TS. TS needs to be fast enough to respect the so-called Nyquist rate of the structure, meaning whatever your highest potential frequency is, you need to sample at least 1 over that frequency, at least that fast for these bounds. We'll get into ways of compressing that in a few minutes. After you've defined TS, our results will depend on a parameter called delta F. This is looking at all the modal frequencies, which are unknown, right? But whatever the modal frequencies are, take the closest pair of them, scale that by TS. That's going to give you a number between 0 and 1. Close to 0 is kind of bad. That actually makes the inference harder, and we'll see how our analysis reflects that. And closer to 1 would be kind of the good case there. So if we're collecting these samples uniformly in time, here's one thing we can guarantee. As long as the number of time samples m is sufficiently large, then we can guarantee an approximation quality between the kth true mode shape and the estimated kth mode shape. So up here, what this is saying, the number of time samples, this symbol means needs to be greater than a constant times the thing on the right-hand side. On the right-hand side, we just have a logarithmic dependence on the number of active modes. We have 1 over epsilon, where epsilon controls kind of the accuracy down here. We'll talk about that in a second. And then delta F is that minimum separation parameter. That's going to show up in every theorem today. The smaller delta F is, then the bigger m needs to be. Larger m means you have to sample for a longer time. This is one of those sort of fundamental phenomena in signal processing. Like if you have two sinusoids that are very close in frequency, you have to wait a relatively long time, right, for them to get out of phase with each other so that you can kind of distinguish them. That's the intuition here of why small delta F would mean a large value of m. When you satisfy this condition, here's the guarantee. Both of these vectors have unit norm, and we're measuring the correlation. We'd like that correlation to be close to 1. And the deviation from 1 scales like epsilon squared. That's the main term here. So if you want that to be smaller, you pay a price in your measurements right here. And this big expression on the right is basically measuring how well separated is the kth amplitude, AK, from all the other unknown amplitudes of the structure. It's a weird property, but it does actually affect the performance of POD. But that could depend on the initial conditions of your structure. If you have two amplitudes that are close to each other, that can make it difficult to distinguish the corresponding mode shapes. One assumption that this particular bound depends on is that the true mode shapes are actually mutually orthogonal. A reason that's necessary here is because the estimates that come out of the POD are actually orthogonal, right? The left singular vectors of the data matrix have to be orthogonal. So for this to kind of work well, the true mode shapes themselves would need to be orthogonal. Some structures do satisfy that. If the mass of the structure is uniformly distributed across each one of your sensors, you can get orthogonal mode shapes. Or if you know things about the mass distribution, you can renormalize your data to orthogonalize the mode shapes. But more generally, this assumption would not actually hold. So here's the same bound just summarized, right? If m satisfies a certain bound, then the error scales kind of like epsilon over this separation parameter of your amplitudes. So we now looked at ways of compressing the data. Is it possible that you could take this data matrix and compress it somehow and still be able to infer the parameters? So sometimes the answer is yes, and the compression scheme we looked at involved random sampling of the columns of this matrix. Or in other words, remember each row is a sensor. So what this means is, what if this sensor only sends this value and this one and this one and this one to the central node? Actually, it doesn't even need to measure the other values. Just measure the red ones and then send those to the central node. So, and we'll let m prime be the number of measurements that each sensor is keeping and transmitting. So we can actually guarantee that this works too. It turns out we basically need the same condition on m, the number of uniform time samples. So kind of underlying all of this, you've still got to sample your structure for a potentially long enough time. But within that, the number m prime of non-uniform samples that you actually need to keep is potentially smaller. It needs a scale like k log k over epsilon squared. And then we get the same kind of error bound we had before. So the question is, when is this bound smaller than this one? And in general, that can happen when delta f is small or potentially small, right? If you need to watch your structure for a long enough time, then you may be able to get by with a number of non-uniform samples that's smaller than what regular Nyquist rate sampling would demand. In other words, you still may need to watch it for a while, but you don't actually need to measure that many values over this time span. That's kind of the takeaway here. Yeah?
Intuition why delta F falls out?
Yeah, I guess the best intuition I could give, well, I'll sketch the proof in a moment, that might help, but I think it's just because the number of parameters we're really trying to estimate is kind of proportional to k here at each sensor. And so, you know, the really kind of the number of actual samples you need, it's nice when you can guarantee that that just scales with your number of degrees of freedom. So here's kind of a sketch of why this works. So here's our data matrix X. And remember our equation of motion here, that X could be written as a combination of mode shapes with these sinusoidal weights, and here's your amplitudes. Just plugging that equation directly into this matrix, it follows that there's a way of factorizing X into a product of this thing, which has just got the true mode shapes as its columns, times this matrix, which is diagonal, times this one, which contains sampled sinusoids. Each row is a sampled sinusoid. The first one has frequency F1, and the last one has frequency Fk. This is not an SVD, but it looks a lot like an SVD, and it would be an SVD if this matrix actually had perfectly orthogonal rows. And so the proof really relies on arguing that the rows of that matrix are approximately orthogonal and using kind of matrix perturbation theory to conclude that the actual left singular vectors of the matrix X will be good approximations to the true mode shapes here. So the prescription on how big M needs to be is really to make these rows sufficiently orthogonal. And the prescription on the number of random time samples, M prime, was also to make these rows kind of sufficiently orthogonal. We looked at one more compression technique here. This looks a lot more like kind of standard compressive sensing. We said, what if each sensor, here's the data collected by sensor number 1. What if that sensor multiplied that data by some random matrix, say M by M prime? That's going to shorten the data vector to this kind of compressed vector that you see there. You do that at sensor number 1 and you send that to the central node. Sensor 2 does the same thing, and each sensor does that, and then the central node just collects this compressed data matrix. You can actually apply the SVD directly to that compressed data matrix, and the number of compressed measurements that each sensor needs to keep is about like it was before. We actually get rid of the log k here. We have k over epsilon squared. So this can work about as well as random time sampling, and it's this scheme that we'll demonstrate here on this real data. So again, we have this data from the telegraph bridge. This bridge does have damping, does not necessarily have perfectly orthogonal mode shapes. There was presumably noise in the sensors and so on. So this violates a lot of the kind of idealized assumptions we've been making. We had access to data from 18 sensors, so this was 18 here, 3,000 uniform time samples, this was 3,000. As we said earlier, we know there's 3 dominant mode shapes in the data, and we compress that big 18 by 3,000 matrix down to just 50 measurements per node. So this is now 18 by 50. And just keeping that 18 by 50 matrix, we want to estimate the mode shapes of the structure. Since there's 3 mode shapes, there's 3 plots on this slide. First mode shape is here. The blue represents our best estimate of the ground truth, the real mode shape of the structure based on all the data using the popular technique called FDD. The black just shows kind of a naive compressive sensing technique where we try to reconstruct each signal separately from the compressed measurements and then apply FDD. That doesn't work very well. And the red shows what we get when we just take one SVD, this 18 by 50 matrix, take one SVD and look at the first 3 left singular vectors. Those are plotted in red on these plots. They have very good agreement with the so-called true mode shapes, and the correlation between the estimated and the true mode shape is quite high, quite close to 1. We were told that this is, good enough to be useful in structural health monitoring applications, this level of agreement. So the POD is this widely used technique. It is very simple to compute. One nice feature is that it supports randomized compression. One limitation, though, is it doesn't allow us to recover the modal frequencies of the structure. So we'll talk about a technique in a minute that can. It only gives us kind of approximate guarantees for recovering the mode shapes. And even then, we have to assume that the mode shapes are orthogonal. So the second method we'll look at here is based on a little bit more of a modern approach, the approach that's kind of more in line with the thinking that's evolved from the compressive sensing community over the past decade. Here's the perspective on this. Let's think of our data matrix, X. If we just look again at those equations of motion, we realize that instead of factoring X into a product of matrices, we could also view it as a sum of matrices. And those matrices are each rank 1, we'll have k of them. Each of them can be constructed by taking the true mode shape, phi k, outer product with a row vector, which again looks just like samples of the kth sinusoid, the kth unknown sinusoid. So this is not earth-shattering, but it turns out to be very important, right? So X, of course X has rank k, the way we've set it up, but not only is it rank k, but it can be written as a sum of rank 1 matrices, where those rank 1 matrices have a very particular structure. So you can imagine asking, well, if I had X, is there a way of figuring out what that decomposition is? Figuring out how to break it into these structured rank 1 matrices. And in this compressive sensing sparse inverse problems community, we can come up with such decompositions, often when we have some kind of sparsity-inducing norm. And that's what has been developed here. It's called an atomic norm in this setting. The atomic norm says, for any matrix X, think of all the possible ways you could break that into this structured sum of rank 1 matrices. All the ways you could build it as a sum of a unit vector, call it bk, outer product with a sampled sinusoid. Of all the ways you could write X in that form, look at those coefficients, find the one with the smallest L1 norm. That defines an actual norm over the set of matrices, and we call that the atomic norm in this context.
So there the frequencies are known or?
Unknown. Right, it does say Fk there, but think of them here as being just completely arbitrary. Of all the ways you could actually build up your signal, your matrix. it turns out that the sparsest one, right, the way you can do this that has the smallest atomic norm is the correct one, is the one with the true modal frequencies, under the assumptions we'll lay out. So the algorithms I'll talk about in a second involve actually minimizing this atomic norm, figuring out these decompositions. That can sound like a really hard thing to do, but it turns out that it's made feasible by a convenient mathematical fact. This atomic norm actually is equivalent to the solution of a certain semi-definite program, which is down here. So semi-definite programs are one of those classes of optimization problems like linear programs, right, for which there's certain general purpose tools available. But here's the overall framework, that we will either have X, or more generally we might have samples of X or linear measurements that we call L of X. What we'd like to do is search over all matrices X prime, say that agree with our measurements of L of X. We'd like to find the one that has the smallest atomic norm. That can be solved by kind of using this correspondence with the semi-definite program I just talked about. And actually, some solvers for that will give you the dual solution of that optimization problem. It's actually from the dual solution of that problem that you can localize exactly what the frequencies are that are the active ones in that decomposition. And once you've got the frequencies, then everything else is kind of a standard least squares problem. It's kind of a linear inverse problem at that point that you can solve for the rest of the unknown parameters. So we were not the first to consider this, and so the rest of my talk will be kind of a survey of different compression techniques and some of the results for these techniques, some of which will be ours, and some of them will be surveying prior work, for example, by Yang and Shi and Li and Chi. And in all of these cases, we'll be talking about guarantees for exactly recovering the mode shapes and exactly recovering the frequencies from these compressed samples. So no more approximate guarantees like we used to have with POD. We're going to be guaranteeing exact recovery with the atomic norm. So going back to this uniform time sampling, Yang and Shi showed that atomic norm minimization can exactly recover the mode shapes and frequencies of the structure. You do actually need about the same number of measurements that you had in POD. We do lose the dependence on epsilon because there's no accuracy parameter anymore. We're talking about exact recovery. And Yang and Shi showed that we can drop the assumption on the mode shapes being orthonormal. This theorem by Yang and Shi actually works for arbitrary mode shapes. So with uniform time sampling, we can do better using atomic norm minimization than POD. Similarly, with synchronous random sampling, where every sensor is just keeping m prime samples in time, atomic norm minimization, we still need to watch the structure for about the same length of time we needed with POD. But within that time, we can take a number of samples that's essentially proportional to k, the number of active modes, or the number of degrees of freedom at that structure. About the same kind of guarantee we had with POD in terms of the sample complexity, but now it's giving exact recovery of the mode shapes. Mode shapes don't need to be orthogonal, but the analysis in this paper did use a randomness assumption on the mode shapes because they're kind of using a probabilistic argument to come up with this result. So that's one area where it would be nice to drop that randomness assumption. We can also think about doing asynchronous random sampling. What if all these sensors collect their samples at different times? Li and Chi were able to derive a very similar result in terms of the sample complexity. That again gives you exact recovery of the mode shapes and again assumes randomly generated mode shapes. They don't have to be orthogonal, but it does follow this probabilistic construction.
So you mean exact with some probability?
It is exact with some probability, that's right. There is a chance that this could fail. It's controllable in that the failure probability delta shows up in the sample complexity, so you could, if you want to decrease that probability,
Yeah, but that's like your epsilon you had before, right?
so you could replace approximate recovery with exact, but some chance of failing. Yeah, guaranteed approximate recovery versus, probable exact recovery. Yeah, good point. Good point.
Is
Thank
your is your distribution on the random mode shapes, does it Does it fit sort of what you typically see in a physical system?
So there's different assumptions that are made. Some of them assume the mode shapes are like drawn randomly from the unit circle or the unit sphere, which I think is not a very reasonable assumption. With that said, the actual performance of these tends to not really rely on that randomness. So I think these techniques are effective far beyond what that randomness would suggest. But in most cases, there are counterexamples. You could construct kind of a malicious set of mode shapes that could potentially break the algorithm. So we looked here at random temporal compression. Remember, that's where each sensor compresses its data vector down to a shorter vector before it sends it to the central node. We assume here that each sensor uses a different compression matrix. So each one is using a different matrix to compress its data. But under that assumption, we were able to derive, again, a similar complexity result. The number of measurements that each sensor needs to keep just scales proportional to k, the number of active modes at that sensor. One thing that was significant about this result is this is the first one to kind of correctly reflect the fact that as we take more sensors, if n increases, we're taking more let's say we're adding more sensors to our structure. In one way, the problem becomes harder because you're adding more unknowns. You don't know the mode shapes at these new locations. But in one way, the problem is becoming easier because the modal frequencies are not changing, and you're getting more and more data about these same frequencies. So experiments also suggest that in a way the problem should become easier. You could reduce the number of samples at each sensor if you're adding more sensors. And that is reflected in our bound. If n is increasing, then for the same probability of error, you could decrease m prime, the number of samples at each one of your sensors. On the other hand, these previous results, when you look for the dependence on n, it's showing up here in your sample complexity. So if your number of sensors went up, then each sensor would need to take more measurements in order for that to work. Finally, we looked at one last compression technique. We call this random spatial compression, in contrast with the random temporal compression. And so here's the idea. So imagine that everybody in this room was a sensor, and all at the same time we collect our displacement value. Now everybody multiplies that value by a random number, which I would also need to know to decode all of this. And then everybody shouts their number to me at the same time, right? And as I hear this, my ear is able to add up all these numbers to just give me the one number, the sum of all these things. Okay, so that wouldn't really work as described, but in phase-coherent analog communication systems, this is plausible, that you could have antennas sending things out in this way that add constructively or destructively as they get to the central receiver. That was originally proposed in the compressive sensing literature as what was called compressive wireless sensing. And we studied the potential performance of that here. So what that would do is take our data matrix, it would compress each column down to one single number, giving us, instead of an n by m matrix, a 1 by m vector of compressed data. And it's just from that single vector that we could apply this atomic norm algorithm to try to estimate the mode shapes and frequencies. And we showed that that could succeed, that m can't be any smaller than before, still needs to be at least 1 over delta f. It also needs to scale at least with k times n. So k times n is the total number of unknowns that we have in this problem, if you count up the mode shapes and frequencies. But one thing that's interesting about this is that it could be that this first term dominates the second one. In other words, once you've satisfied your kind of Nyquist type sampling and you've observed your structure long enough, then within that time span, you may be able to just compress your entire data matrix down to this one vector, and from that vector be able to recover the mode shapes and the frequencies. This did have a randomness assumption on the mode shapes in order to prove this. So we've surveyed a lot of different results and setups. I want to just spend the last few minutes kind of summarizing things. What are the main themes or takeaway messages from all this? So theme number one, when delta F, when your frequency separation is small or potentially small, all these methods require you to sample over a sufficiently long time span. But during that time span, there's various ways that you can compress the data or subsample your data and not keep all of the Nyquist rate samples. We looked at an experiment here with 5 sensors and 3 active modes. We constructed random mode shapes, but we made sure that 2 of them were somewhat correlated with each other. And we looked at the best way of spending 100 total samples or total measurements across everything in the sensor network. With all the random sampling and compression techniques, we saw a high probability of successful recovery with both the frequencies and the mode shapes. They all spread their measurements over a total of a 5-second period. So they were sampling long enough in time to account for the separation between the 2 closest frequencies. We looked at a couple of different ways of doing uniform sampling. One where each sensor takes 20 samples over just a 1-second period. So that's too short. It's not kind of respecting this time duration bound we have because of the frequency separation, and we see that both we fail to recover the frequencies and the mode shapes there. And then we said, well, what if we just spread out those uniform samples? We'd have to slow them down, but we spread them out over 5 seconds. Well, there we incur aliasing. So when you're sampling too slow compared to Nyquist rate, that causes us to miss out on the frequencies. Interestingly, we can still recover the mode shapes when we do that, but we cannot recover the frequencies. Second takeaway is that in all the sample complexity results for atomic norm minimization, the number of samples we need to take, if you just count up everything in the network, it always scales linearly, maybe with some additional log factors, but the essential scaling is linearly with the number of active modes and the number of sensors that you have. So kind of the total number of degrees of freedom matches the sample complexity in all of these results. This is just an experiment with 10 sensors. We took 100 uniform samples originally and we compressed them down to 10 samples per sensor. And we said if we add more active modes, we compressed them down to M prime samples per sensor. That's the vertical axis here. And we said with different numbers of active modes, how many samples do you need in order to recover the mode shapes? And that's reflected here in this kind of line separating successful recovery from failure there. And it's the fact that this is basically a line that is showing that linear dependence between sample complexity and kind of number of degrees of freedom. Third takeaway concerns orthogonality, right? This POD method only returns approximate solutions, and it's most accurate when the mode shapes are orthogonal. Here's 2 experiments. On the left is one with orthogonal mode shapes. The true mode shapes are shown in red, and the POD estimates are shown in blue. They're pretty good. On the right is the same experiment with non-orthogonal mode shapes, and we see some deterioration in the results. The atomic norm minimization performance is shown in black for both plots, and that is working exactly, giving us exact recovery of the mode shapes. Synchronous versus asynchronous sampling, is it better to take, when you're doing random sampling in time, is it better to have all the sensors sampling at exactly the same time, or is it better to kind of let them choose their own random sample times? The theory on that is currently inconclusive. It doesn't give a clear indication one way or the other. Experiments suggest that asynchronous random sampling is better, which I think agrees with intuition that you may have correlations in what you're seeing from one sensor to the next. So why should they be all sampling at the same times, right? And you might get more diverse measurements if they're sampling at different times. It would be nice to have some theory that supports that. And I talked about the fact that as we add more sensors, the problem should become easier. Here's one experiment to demonstrate that. We started with 80 uniform samples, and we compressed down to just M prime samples at each sensor. The different solid curves show the probability of successful recovery for 2 sensors, 4 sensors, 8 sensors, and 16 sensors. And in fact, we do see that the problem is becoming easier because those curves are moving up and to the left. On the other hand, what would happen if we tried to process these signals separately? So do just frequency estimation at each one of your sensors separately and see if they all agree at the end. The likelihood of that happening just goes down, of course, as you add more and more sensors. So this highlights the benefit of kind of joint processing. I'll just quickly mention some additional recent work. I mentioned we had been doing other related problems with Gongwo Tong and also with John Helland, who's here. We've been looking at extending this atomic norm framework to account for damping. And the idea there is based on just looking at this equation, right? If you have, say, a signal that's a sum of sinusoids, but each one is damped by this exponential term that's decaying over time. We could think about this as like a regular sinusoid that's been multiplied by some function. In this case, it's an exponential function. We can extend this atomic norm framework, this dictionary, to allow sinusoids that are multiplied pointwise by functions. We need those functions to satisfy assumptions like living in a subspace, but we can extend our framework to estimate those as well. And then one other recent project with Schwang, we've been looking at the related kind of music algorithm for spectral analysis. And we've identified some connections between that and the sort of optimization themes that you saw in this talk, which allowed us to extend that music algorithm to accommodate random sampling. I don't think I have time to go into that, but I'd be happy to talk more about that offline. And if you're interested in following up on any of this, here's the papers that summarize the main results from today, but I'll be happy to stick around or answer any questions people might have. So, thanks again for your attention. I appreciate you coming.
I think we have time for 1 or 2 quick questions.
Thanks a lot. I really enjoyed the talk.
Thanks.
I wanted to, so my question is sort of about the end product.
Okay.
Let's suppose that an engineer has to make a decision whether to shut down the bridge or do a very thorough inspection of it.
Mm-hmm.
It seems like if you're thinking about that endpoint, there may even be more opportunity to compress the signal just to produce that kind of warning signal. Have you
Right.
thought about that at all?
No, I think we haven't really pushed this towards the kind of downstream processing of, say, these modal parameters. I think that's a really interesting problem. There's been a lot of other techniques there too, like machine learning, for example. You might apply some kind of neural network to the types of mode shape estimates that we're getting here.
Okay.
But we haven't actually thought about like what would be the theory behind that, really.
Okay.
How reliable could you be if you were giving that binary decision? It's a really interesting question.
Although if the unhealth of the structure is related to a subtle frequency shift,
Mm-hmm.
I mean, your analysis is great for that because you can understand what you can detect there.
That's right. Yeah, we sort of can at least understand about the specific parameters that we're talking about. That's right.
Do you need to know what K is, or that's maybe you just pop out of it out?
Yeah, that's also a good question. So I think you might know it. I mean, when you're doing some initial assessment of your structure, probably even your original modeling and computer design and things like that. But of course, surprises could happen. I mean, depending on how bad the damage is, nonlinearities could happen, and a lot of assumptions could fall apart. But that would.
You started off by motivated. I think it was motivated with the second order ODE.
Mhm.
I mean, is that still lurking here, or is that something that you've now thrown away?
No, I think that's lurking here. I mean, if the structure obeys that equation, and if we assume that there's no forcing input and no damping, then the actual time evolution of your signals will be the combination of sinusoids that we talked about here.
So that's probably a big assumption, right, for a bridge.
Yeah.
We need one single ODE. I mean, I know people do this for
Yeah,
beams representing
Mhm.
buildings and things like that.
I think it depends on how complicated the structure is. Yeah, I think it seems to be reasonable enough that people apply these modal analysis algorithms to large structures. Now, if somebody were asking me to plug this into a real system, I'd say let's talk a little more to some civil engineers to make sure this is all justified.
All right,
One more
Steve.
real quick, just to follow up.
Ganesh, check that.
So, just to follow up a little bit more on that, so you're currently working to kind of generalize the free undamped problem to
Yeah.
free damped problem.
Mhm.
And I think that's certainly that's going to be a step more in the realistic direction. But the forcing is the thing that kind of concerns me more than else. Is
Yeah.
if you started looking at this, because any structure you look at, things are going to be happening on top of the structure of the bridge, right?
Yeah.
And so that's going to be changing the natural frequencies and things like resonance that can occur,
Yeah.
at least in theory.
Yeah, so it's been a little while since I looked at that. As I recall, I mean, the frequencies themselves may be somewhat robust to that. The POD method is surprisingly effective. It's very simple, but it may actually still stand up well in that setting. So there are plenty of techniques available for modal analysis with forced inputs, but it's totally true that we haven't been studying those in this. I would really love to have a nice theory for like extending this atomic norm minimization to settings like that, but it's not something that we currently know how to do.
Ganesh?
POD-based approach in general, under random setting, depends a lot on the correlation of particular variance. So if your variance is a little larger, just the system becomes bigger and bigger.
Mm-hmm.
So there's a hidden thing about people play around with it by having a low variance, so that you can manage a good situation. Is that's hidden part? Right? That's in general true.
Yeah,
Because you're single
sorry, I'm
values,
not
right?
quite sure I followed.
So if you have your singular values,
Singular values.
yes, that's right. Your singular values, essentially the whole thing depends on the magnitude of the singular values. So
Sort of, you mean the robustness to noise might depend on how
yeah.
energetic your signals are?
Exactly.
Okay. Yeah.
And then that's where the variance come into picture. Yeah.
Mhm.
So when you have that, so for the low variance case, I think that's what you're doing it in terms of difference between the frequencies, as long as it's low.
Yeah, I think that's different. I mean, to be clear, we're not actually talking about measurement noise here at all. Although numerically we saw POD is robust to that. And I didn't mention it, but we have extended our theory for some of these problems, the atomic problems, to include noise. You change the algorithm a little bit, you can handle noise. But that frequency separation is something else. I mean, it is like a different kind of ill conditioning in a way. It's sort of like the condition number of a matrix. I think I would draw that connection to it.
All right, so let's thank our speaker once again.